We have defined vector spaces, subspaces, sums, and direct sums. Now we need two new words that quietly run the entire subject. Those words are linear independence and span. Charming names. If you enjoy terminology that sounds innocent before it starts assigning homework. A list of vectors is linearly independent if the only linear combination that gives the zero vector is the one where every scalar is zero. In less ceremonial language, no vector in the list is secretly redundant in a way that helps build zero. If zero can be made using non-zero coefficients, then the list is linearly dependent. That is algebra's way of saying someone in the list is freeloading. For example, in R2, the vectors 1, 0 and 0, 1 are linearly independent. A times 1, 0 plus B times 0, 1 gives A, B. So if that equals 0, 0, then A and B must both be 0. No sneaky cancellation. How disappointingly well behaved. Now span. The span of a list of vectors is the set of all linear combinations of those vectors. So span is not one vector. It is the entire collection of vectors you can manufacture from the list. It is basically the algebraic factory generated by your vectors. Very industrial, very underpaid. For a simple example, take one vector, 2, 1, in R2. Its span is every scalar multiple of that vector. Geometrically, that is the line through the origin in the direction of the vector. The origin is included, because scalar 0 ruins every party. Now finite dimensional. At this point, we define it only using span. A vector space is finite dimensional if some finite list of vectors spans the whole space. Important. We are not defining dimension yet. That comes later, after we prove the definition is not a trap wearing a fake mustache. For a finite dimensional example, R2 is spanned by 1, 0 and 0, 1. Every vector x, y in the plane is x times 1, 0 plus y times 0, 1. For an infinite dimensional example, take the vector space of all real polynomials. Any finite list of polynomials has some largest degree. It cannot span a polynomial of higher degree. The higher degree polynomial simply strolls past the security gate. In this series, we will mostly focus on finite dimensional vector spaces. Infinite dimensional spaces are important, but they belong more naturally to functional analysis. Let that future headache remain politely in the future. The next goal is to prove that dimension is well defined for finite dimensional vector spaces. We will build toward bases, and then prove that every basis of the same finite dimensional vector space has the same length. Only after that proof will dimension deserve to exist mathematics, where even counting has to pass a background check.